All right, so here is our last video for our kinetics unit. And in this video, we are going to take a closer look at catalysts. So we have a pretty good understanding of a catalyst. We know that we can add them to the reaction and it will result in a quicker reaction because it will change the reaction mechanism to one that has a lower activation energy. And once we have that lower activation energy, then more of the molecules can overcome the activation energy. Therefore, we can have more successful collisions and a faster rate. One thing that we haven't talked about previously too much is that the catalyst is added to the reaction and is consumed and then produced back. So it's there at the beginning, it gets consumed, and then it gets produced back, so it's there at the end. Since it is there at the beginning and there at the end, it does not appear in the overall reaction. So if we take a closer look at this example here, we have the reaction between NO2 and carbon monoxide to produce NO and carbon dioxide, and we have the rate law. And then they give us the two-step reaction mechanism. So first thing we want to do is write the equation for the overall reaction. So we just sum those up. So we would have 2 moles of NO2 plus NO3 and CO. So all I did was combine all of my reactants. And then I'll combine all of my products. So NO, NO3, NO2, and CO2. Then what I want to do is I want to simplify this by crossing out anything that appears on both sides of the equation. So that would be NO3 because it shows up on both sides of the equation and one of the NO2s. And you could have done this prior to summing up the two reactions. So then that would end up giving me NO2 plus CO makes NO and CO2. Now, obviously, at this step, it should still be balanced. So we can quickly check that. One N on both sides, 3 O's on both sides, 1 C on both sides. So if this was unbalanced, that would be a huge sign that we had made a mistake in there. Okay, now they ask us for the intermediate, and we've already talked about intermediate. So intermediate gets produced and then consumed. So that would be NO3 because we produce NO3 in the first step and then NO3 gets consumed. So therefore that would be an intermediate. A catalyst is a little bit different. A catalyst gets added in the beginning, used up, and then consumed. And then produced. So a catalyst gets added in the beginning, used up, and then produced. So it's still going to get crossed off the equation, but in a different manner. So that is going to be NO2 because I added it and it got consumed and then it got produced. So NO2. So basically it's the two things that we crossed out. The NO3, that would be the intermediate, and one of the NO2s, that would be the catalyst. Lastly, what can we say about the relative rates of step 1 and step 2? So our rate law is K times the concentration of NO2 squared. Therefore, the step 1 must be the slow step because step 1 is the rate determining step because the rate law matches step 1. So if we had to explain it further, then we would say because the rate law matches step 1. So step one must be slower than step two. Step one must be the rate determining step. All right, so we have another example here. So this is a four-step mechanism. And notice they tell us the first step is slow. So the first step would be the rate determining step, and then we have our other steps. So write the rate law for this equation. Well, that would have to be based upon my slow step, the rate determining step. So K times the concentration of HBr to the first power times the concentration of O2, also to the first power. And HBr and O2 are both in the overall equation, so everything is legal about my rate law. I don't have to do any substitutions. List all intermediates in the reaction. So intermediates are things that we produce and then consume. So that would be HOOBr. We produce it in step one, then consume it in step two. Now we should check, see if we have anything else that also would be an intermediate. We would have the HOBr gets produced and then consumed. And actually both moles of it get consumed. One in step one, one in step three. So HOBr is also an intermediate. So those are not going to show up in my overall equation. And that would be it for my intermediates. Now I want to see if there are any catalysts. So a catalyst is present at the beginning, gets consumed, and then gets produced somewhere in a later step. There are no catalysts in this problem. So the only things that we crossed off were intermediates. So a catalyst would have to be one of my original things, HBrO2, and neither one of those got produced back. So we have no catalyst for this reaction. Lastly, we have a quick review of Beer's law because we use this a lot of times with kinetics. So a spectrometer can be used to measure the change in concentration of a reactant or product during the course of the reaction, assuming that that reactant or product has a color to it. So it's something other than a clear solution. So it measures the amount of light absorbed by the sample and how that changes over time. So if we start with a dark blue solution and it gets lighter, the amount of light that it's going to absorb will change as its concentration changes. And this formula is on our reference table. Although they have updated the reference table, instead of little a, it is now epsilon. So that actually makes it a little less confusing because we don't have big A and little a in there. So it is now epsilon. But the equation is the same. A is the absorbance that we would measure. That is directly proportional to the concentration, which would be measured in molarity. B is the path length of the cuvette. Normally that is 1 centimeter. And the molar absorptivity constant, epsilon, that's something that we would have to calculate or be given. So we'll take a look at this example here. So we are told in the problem that it is a first order reaction. And we are measuring the absorbance of a colored, so something other than clear, solution at 520 nanometers. The reaction occurs in a 1 centimeter sample cell, so the path length is 1 centimeter. The only colored species in the reaction, so there's nothing else that would change the absorbance, and they give us the molar absorptivity constant. So we are calculating the initial concentration of the solution at the beginning of the reaction. So our original absorbance is 0.605. The molar absorptivity constant is 5.6 times 10 to the third per molarity per centimeter. The path length of our cuvette is 1 centimeter, and we are looking for the concentration. And once we plug that into our calculator, we get 1.08 times 10 to the negative fourth for my original molarity. All right, then in our second calculation, so this is all the same, just copied over so that we have all the information there as a reference. So in our second part here, the absorbance decreases after 30 minutes. Now that makes sense because the concentration is going to decrease over time. So as the concentration decreases, the absorbance would also decrease. Calculate the rate constant in units of per second because it is a first order reaction. All right, so this one is a little tricky. So we have to think about the information that we have. We know it's a first order reaction. So we could plug this into our natural log equation from the reference table. We do have our initial concentration from the previous problem, and we can figure out, using Beer's law, our concentration at 30 minutes. And then once we have the two concentrations, then we can plug it into the natural law equation. So first thing we have to do is plug it into Beer's law to figure out what our concentration is at 30 minutes. So the absorbance is equal to the molar absorptivity constant, which is 5.6 times 10 to the third. And the path length is 1 centimeter. And then we are looking for the concentration. So we plug that all into our calculator and we get a concentration of 4.46 times 10 to the negative fifth. So this is our original concentration. This is our concentration after the 30 minutes. It makes sense that it is lower. So once we have those, then we can plug everything into the natural log equation. Now remember that's the natural log of the concentration of A at time t. So that would be this new 4.46 times 10 to the negative fifth minus the natural log of the concentration of A originally. So that would be the 1.08 times 10 to the negative fourth is equal to negative KT. Now, T is 30 minutes, but they wanted it per second. So we should plug that value in as how many seconds that would be. And that would be 1,800 seconds. All right. So then we do all of our math, get the value for the natural log of the first one minus the value of the natural log of the second one. Then divide both sides by the 1800, and that gives us a value of K as 4.91 times 10 to the negative fourth per second. So this problem was a little complicated. We had to use Beer's law and the natural log equation in there. All right, and then our last part, calculate the half-life. We can just use this formula off of the reference table. So half-life for a first-order reaction, and it is a first-order reaction, is 0.693 divided by the value of K, which we just found in our previous problem. So then we just need to plug that all into our calculator, and that will give us the half-life, and that will be in seconds. All right, once I plug that into my calculator, I get 1,411 seconds. And let's see, how many significant figures do I want? Looks like I want 3 significant figures, so 1,410 seconds would be the half-life, the time it would take for half the concentration to decrease.